In this section, we'll describe the various statistical tests that one can use to compare populations. You should feel comfortable by the time this section is over in deciding which statistical tests will apply to which situation. The most important thing you can look at in making this decision is the type of variable involved. Is it going to be a qualitative or a quantitative variable? This will guide you into what direction you will go into in terms of making your statistical determination. The four main tests we'll discuss here are correlation, chi-square, t-test, and ANOVA. Correlation. Correlation measures the relationship between two groups of variables. The degree of correlation between these groups is described by the correlation coefficient, often given the variable name R. And R, which is the correlation coefficient, ranges between -1 and 1. -1 would be seen if there were a perfectly negative correlation. 1 would indicate a perfectly positive correlation. 0 connotes no correlation. The next slide illustrates examples of different types of correlation. On the left, we see a perfectly positive correlation, and on the right, we see a perfectly negative correlation. For example, given the following data of height and weight, one could ask, is the weight of an individual in the following population related to his height? Well, one might assume that that's the case, but we can test this more specifically by plotting out the various heights and weight to see how well correlated they are. The next slide shows the data, and it certainly appears that as the height increases, the weight also increases, and vice versa. Now, one might ask, first of all, which of these two values should be plotted on the x-axis, which should be plotted on the y-axis? And the answer is, it doesn't matter. Correlations are not specific to one variable correlated against another variable, and there should be no ordering here. So I could have just as easily plotted weight on the x-axis and height on the y-axis, and the correlation coefficient R will be the same. So the correlation in this particular case is 0.87. Now, the other piece of information that can come out of this kind of relationship is a regression line. Now, one must be careful. In a regression line, it does matter which is plotted on the x-axis and which variable is plotted on the y-axis. The regression line is the line that's shown as follows on top of the data in this graph. The regression line has the format of y equals mx plus b, where x and y correspond to the variables on the x and y-axis respectively. M corresponds to the slope of the line, and b corresponds to the y-intercept. The line that is generated that corresponds to what we see here is known as the regression line. This regression line is specific to whether or not each individual variable is on a particular axis. If I were to switch height and weight and to put these on two different axes, I would get a different regression line, but I would get the same correlation coefficient. So please be aware of the difference. Regression lines do depend on whether or not each individual variable is on any given axis. Correlation coefficients do not. How about another correlation? Are USMLE scores related to age in the population? So shown on the table on the right is a series of different ages of people who took the USMLE and their scores. Well, let's plot them out and see what kind of trend we can observe. Well, simply by looking at the data points, there's no obvious trend, and this is confirmed by our analysis of the correlation coefficient of R, which is 0.03. Now, a regression line is drawn here, but it's not particularly meaningful. The slope seems to be pretty close to 0. Now, when correlation coefficients are generated, one can also generate a p-value. The p-value can be applied to our hypothesis test to determine whether or not we reject or accept the null hypothesis. Practice question. A study to assess the relationship between serum glucose and hemoglobin A1C levels as markers of diabetes was performed. interpretation of the data revealed a linear relationship between these two variables and a correlation coefficient of the following: R equals to 0.35 with P equal to 0.005. Which statement about these results is the most correct? A. These results are not statistically significant. B. There is a strong correlation between serum glucose and hemoglobin A1C levels. C. As serum glucose increases, hemoglobin A1C increases. D. There is a negative correlation between serum glucose and hemoglobin A1C levels. Or E. Increase in serum glucose levels cause increased hemoglobin A1C levels. Well, let's think about what the data are telling us. They tell us that R is 0.35 and that P is 0.005. So first of all, P is significantly lower than 0.05, the most common value for alpha. This would imply that these data are statistically significant. What does an R of 0.35 tell us? Well, first of all, it's positive. So this tells us that there is a positive relationship between these two variables, which would suggest that as one variable increases, so does the other, such that when serum glucose increases, so does hemoglobin A1C. It's important to remember what these data do not tell us. They do not tell us anything about causality. So one must be careful not to assume that an increase in one variable causes an increase in the other variable. They are simply statistically related and correlated, but not necessarily causally so. So going through these answers, the most appropriate answer would be C. As serum glucose increases, hemoglobin A1C increases. Answer E would not be correct because of the statement I previously made about causation. And answer B would not be correct because one can't assume anything about the strength of correlation necessarily between glucose and hemoglobin A1C. This is a term that carries some value statements in there, and one may have a different interpretation of strong versus not strong. One can only state that results are either statistically significant or not. The next test that we'll discuss is the chi-square test. And the chi-square test is used for differences in qualitative variables. Typically, when one has qualitative variables, the only data that one can generate from that is proportions. So the chi-square test compares the observed proportions in the groups and compares them to the expected proportions. Commonly, the null hypothesis is that there's no difference in the proportions. Do an example. Let's say that there are 100 people in a room, 40 males and 60 females. 50 are sitting on the right side and 50 are sitting on the left side. If the proportions were equal, and that is to say that males and females randomly chose either to sit on the right side or the left side, one might expect the following data. That is, looking on the right side, one would expect 20 males and 30 females, and on the left side, 20 males and 30 females, because males make up 40% of the total population. What if the actual data looked like the following? And that is, on the right side, there were 10 males and 40 females, and on the left side, there were 30 males and 20 females. Is there a significant difference? Do there appear to be more than what you'd expect to find in terms of males on the left and more females on the right? How do we know whether or not this is simply due to random chance or whether or not there is a statistically significant difference? The chi-square test will guide us. So first of all, you should recognize these variables as being qualitative variables for which we only have proportions to do our analyses. The chi-square test is calculated as follows. Chi-square is equal to the sum of all the squares of the differences between the observed data and the expected data divided by the expected data. Put these side by side. On the left, we have the expected data based on the total percentage of men found in the population, that is 40% men and 60% women. On the right, we have the actual data. Chi-square then is in the sum of all the squares of all of these differences between the expected and the observed data. So for example, the first term is 10 minus 20. This corresponds to the difference between the top left corner of each of these two boxes. and that's divided by the expected value of 20. 30 minus 20 corresponds to the top right corner of each of these two boxes, and so on and so forth. When the whole expression is computed, one gets a chi-square value of 16.7. So what does 16.7 mean? Well, there are standard tables that tell you for any given number of subjects, does a chi-square correspond to a significant value or not. So one can take this chi-square table, go to a chi-square value, go to a table of chi-square values and determine what is the critical value. Well, in a 2 by 2 table, as in the data shown in this particular case, for p to be less than 0.05, chi-square must be at least 3.841. Well, our chi-square value is 16.7, and since 16.7 is greater than 3.841, we can safely reject the null hypothesis and say that the male-female ratio is greater on the left than on the right. In other words, that this difference is not simply due to chance. The test we'll discuss is the t-test. The t-test is used to determine if there are differences between groups containing quantitative variables, for example, the average height in men versus women. This test is used to determine whether or not two distributions of values are equal or not. And it's very important to remember that this test only works for two groups, so t equaling 2. For example, imagine a study in which a group of patients are treated with two different medications for hypertension. Systolic blood pressure is measured for each patient in each group, and the values are compared. And those data are shown in the following slide. So here we have treatment A. We have several patients who were treated and several values of their blood pressure, and similarly for treatment B. We have a mean of 115 for treatment A with a standard deviation of 15, and a mean of 130 for treatment B with a standard deviation of 16. Frequency histograms for these data are plotted in the next slide. So on average, it appears that group A has a lower systolic blood pressure than group B. However, there is substantial overlap between these two groups. So how do we know whether or not there is a statistically significant difference between these two groups? In this case, we'll perform a t-test. Again, we have two groups and we have quantitative variables, so a t-test is the appropriate test to use. This test compares the two groups of values and will tell us whether or not they are statistically different. The output of this test is a p-value, and again, the p-value is the probability of making a type 1 error. The mathematical details of this test are beyond the scope of this review. In this case, we perform a t-test and the p-value is 0.003, which is below our value of alpha of 0.05. So in other words, if we claim that the average systolic blood pressure of group A, which is 115, is lower than group B, 130, then there is only a 0.3% chance that we will be wrong. Since 0.003 is less than 0.05, we can confidently state that the medication for group A is more effective than for group B. ANOVA. So a t-test only works for two groups. If you have an identical format of data, that is, you have quantitative data, but you have three or more groups, you have to use a more complex statistical test known as analysis of variance, or ANOVA. The details of this test are beyond the scope of USMLE, but you certainly should know when to use it. Practice question. A pharmaceutical researcher is examining the ulcerogenic potential of a new non-steroidal anti-inflammatory drug. He gives 20 rats a single subcutaneous injection of the drug every day for 1 week and gives a similarly matched group of 20 animals daily saline injections for 1 week. 24 hours after the final injection, the investigator sacrifices the rats, removes their stomachs, and examines them to determine if any ulcers were produced. Ulcers were found in 12 of the rats who received the drug and 8 of the rats who didn't receive the drug. Which of the following tests should he use to determine if the drug increases the incidence of ulcers? ANOVA, chi-square, linear regression, t-test, or correlation coefficient. As mentioned earlier, the first step in making a determination like this is identifying the type of variables that are being looked at. Well, the variable here is whether or not an ulcer was produced. These are categorical variables, meaning one cannot have half an ulcer or 2.5 ulcers. Each subject, or rat in this case, will either have an ulcer or not. And what we're doing is measuring the proportion of rats who have ulcers. Whenever one is looking at purely qualitative variables and proportions of qualitative variables, the appropriate test to use is a chi-square. So for this question, the correct answer is B, chi-square. Practice question. A pharmaceutical researcher is examining the ulcerogenic potential of a new non-steroidal anti-inflammatory drug. He gives 20 rats a single subcutaneous injection of the drug every day for 1 week, and gives a similarly matched group of 20 animals daily saline injections for 1 week. 24 hours after the final injection, the investigator sacrifices the rats, removes their stomachs, and examines them to determine if any ulcers were produced. Ulcers were found in 12 of the rats who received the drug and 8 of the rats who did not. Which of the following tests should he use to determine if the drug decreased the overall size of the ulcers in the treated group? Well, one must be careful here. You need to look at the variable that's being compared. The variable being compared in this question is not whether or not rats developed an ulcer or not. The variable here is the size of the ulcer. The size of the ulcer is a quantitative variable. It can be measured in whatever units are desired, but those units can be subdivided with an infinite level of precision. Whenever one is looking at quantitative variables and comparing two groups of quantitative variables, the appropriate statistical test is a t-test. For that reason, the correct answer here is D, t-test. Practice question. A researcher now administers a drug to 3 more different strains of mice and observed that 18 of 20, 6 of 12, and 7 of 15 mice in these groups developed ulcers respectively when exposed to the drug in question. The Institutional Review Board wants to study if any of these groups have increased susceptibility in order to exclude them from further testing. Which of the following tests should be used to determine a statistically significant difference? ANOVA, chi-square, linear regression, t-test, or correlation coefficient? Again, this question boils down to identifying what kind of variable are we looking at. In this case, the variable is a categorical variable. We're looking at the number of mice that had ulcers. Whenever you're looking at the number of any individual categorical variable and the proportions of which, the appropriate test is a chi-square. It's important to recognize that a chi-square test does not only have to be comparing 2 different populations, it can compare multiple populations. Importantly, the chi-square test is the appropriate test to use when comparing proportions of qualitative variables as we are here. Next question. A study is conducted to assess a possible association between congestive heart failure and erythrocyte sedimentation rate, or ESR, levels. The data collected is shown below. And you can see the table with CHF, non-CHF, high ESR, or normal ESR, and the various data that are shown. Which is the best statistical method to assess the association? Well, again, despite the fact that we're looking at things that could be quantitative, such as ESR, all of these data have been broken down and split into categories. People who have a high ESR versus normal ESR, people who have CHF versus no CHF, and there's no ability to subdivide these categories. Therefore, we are again comparing proportions of qualitative variables, and whenever you're comparing proportions of qualitative variables, the correct statistical test is chi-square. So for those reasons, the answer is B, chi-square. Here are the important take-home points. If your data is all quantitative, the appropriate test to use if you have 2 groups that you're comparing is a t-test. If you have more than 2 groups, the appropriate test to use is ANOVA. One way of thinking about this is that if you try to use ANOVA for 2 groups, mathematically what you are really doing is simply a t-test. So t-test and ANOVA mathematically are nearly identical. The only difference is in the number of groups that are involved. If one is looking at all qualitative data, particularly if you're comparing proportions, the appropriate test is a chi-square. Correlation testing can be used for any manner of quantitative data and for ordinal qualitative data. Recall that qualitative data can be ordinal or nominal. In nominal, there is no ordering of the data, whereas in ordinal data, there is a natural order to the data. So either quantitative or ordinal qualitative data can be utilized with correlation testing. That concludes this section on statistical tests. Next, we'll talk about applied statistics.